All right, good afternoon. Thanks for attending this talk this afternoon with me. First, start off by recognizing my co-authors, Robert Rice with Geosystems Analysis, Walter Burt with GSI Water Solutions, and Jason Milady with GSI Water Solutions, who's sitting up front here. So today we'll be talking about a project to enhance stream flows in the summertime in a creek in 15 Mile Creek, which is located in the state of Oregon in the United States. This creek and the watershed supports an irrigated agricultural base made up of primarily cherries, alfalfa, and wheat. But within 15 Mile Creek are endangered species fisheries, primarily steelhead and lamprey. And so there are concerns with low flows and the effect on the livelihood of these the fisheries in this creek. In particular, it's water quality limited. So in the summertime, when temperatures are greater and flows are lower, stream temperatures tend to spike, which can be detrimental to the fisheries. So again, a way to combat this is to augment summertime flows and hence reduce the temperatures. And so looking at how to do that. So looking at the location, here we are in Spain, here is Oregon in the United States, in the Pacific Northwest. And then going into a close-in of the study area. The study area is this drainage right here. You can see it's in a semi-arid portion of the state, receives about 32 centimeters of precipitation a year. In the summertime, the temperatures are often in excess of 38 degrees Celsius, so it can be quite warm. You can see that with Oregon, they have a dividing line. This green part is the western part of the state, fairly wet. And then you move on the other side of the Cascade Mountain Range, which is this north-south range. You get to a semi-arid part. This is Mount Hood, which snowpack and snowmelt from Mount Hood and the Mount Hood Basin supplies water to 15 Mile Creek. Now, with increased changes in temperature in the wintertime, we're now seeing an earlier snow melt. And so then we're seeing an earlier hydrograph in 15 Mile Creek. So the whole idea is how can we delay that hydrograph, get it back out into the spring and into the summer with increased flows. So one way of doing that is to look at subsurface storage. And that's what this whole study is about, or the whole study that we looked at was assessing of subsurface storage of this water when there's plentiful water in the stream in the summer or in the winter and the spring, if that can be captured and stored and then either introduced or returned back to the stream, or that water that's stored could be used by irrigators in the summer in lieu of the irrigators diverting water in the summer. So as part of the overall study, we were looking to see if this could be used to improve the ecological function of 15 Mile, again, supply irrigated agriculture. And there's multiple facets of the study. There's regulatory, water availability, suitability of the deep aquifer to store the water, water quality and treatment. We need to treat the surface water before injecting it into the deep basalt aquifer, and infrastructure. However, for this talk, I'll just be focusing on the water quality and treatment component of this overall study. So again, just to show a quick diagram of how this would work with the subsurface storage concept. Looking at recharge of up to over 14,000 liters per minute over a 4-month period spanning from January to April. That's when there is sufficient water in 15 Mile to be able to divert and store based on existing regulations within the state. So the idea being, as a river comes down, you could either divert water off and use a shallow infiltration basin and a shallow collection into the shallow alluvial aquifer, which is hydraulically connected to 15 Mile. Collect that water shallow in the subsurface, pump it out, and then inject it into the deep basalt aquifer, which is a confined aquifer, approximately 300 meters below ground surface. At that point, that water could be then pulled out in the summertime for either irrigation, or as I mentioned, it may be just redirected back into 15 Mile, providing cool water, and that in lieu, and then the irrigators would still be doing a diversion. Other alternatives to this, which are not showing in this picture, is instead of diverting it, and I'll show in the next slide, into a recharge basin, a shallow infiltration basin, also just having pumping wells directly adjacent to the creek. And so, again, I mentioned this alluvial aquifer is hydraulically connected. So if we have shallow pumping wells, you can pump and induce recharge through the stream bed and have aquifer filtration that way. So aquifer filtration, I won't spend much time here. We're all familiar with that. I know there's been a number of talks about it over the last 2 days, but it's a cost-effective way to remove suspended solids, biodegradable material, microorganisms, macronutrients, and and heavy metals. Now, why this is very critical here is for aquifer storage and recovery to really be economically feasible is you have to have a low-cost way, a cost-effective way to treat the surface water. This is in a non-municipal area. There is not water treatment infrastructure nearby, so that to build a water treatment facility to treat the water would immediately make ASR not possible for storage. And so that's why this is such a critical component of the study. Now, just the basic question is, can sufficient volume of water of adequate quality be cost-effectively diverted or collected from 15 Mile over this 4-month period? And I mentioned just earlier that we looked at 3 alternatives. Alternative 1 is having a shallow alluvial aquifer well, again, it's hydraulically connected to the river, pumping from that well, inducing recharge through the stream bed, and having aquifer filtration. So then at this point, this water that's removed would be injected into the deep basalt aquifer. Alternative 2 would be a horizontal well, perforated well that runs parallel to the stream bed, same idea. We would have water inducing recharge through the stream bed, collecting it, and then from there removing it and directing it into the basalt aquifer. So these 2 methods are somewhat passive. Alternative 3 is more of an engineered method in that we would then be diverting water off the stream into a spreading basin, which underneath would be a collection system that the water would be then collected, and then from there diverted to the injection well. So as part of this study, there's very little information about the alluvial aquifer. The alluvial aquifer really is not utilized in this area. So we had to develop a characterization program to understand the hydraulic properties of the alluvial aquifer, to know how much could we pump from that aquifer over the 4-month period. So we developed a characterization program to look at the stratigraphy of the alluvial aquifer, the hydraulic properties of the alluvial aquifer, and determine the aquifer thickness. From that information, we then did analytical modeling to look at potential collection rates, as well as collecting surface water and groundwater samples for quality testing. The characterization program consisted of test pitting and geological logging, 25 test pits. Alluvial aquifer test wells were drilled and installed, from which we did slug testing and collected some samples. Single ring cylinder infiltrometer tests with lateral divergence correction were also performed to look at the near surface hydraulic conductivity, which helps guide potential for infiltration basin, the surface engineered basin, and then laboratory testing as well to look at physical and hydraulic properties. The aquifer collection rate model is a 2-dimensional analytical model for a pumping well near a connected stream. Some simplifying assumptions with this model is that alluvial aquifer was an infinite extent. In our instance, we were limited to a certain area where these wells would exist, and that was 6 meters from the creek. And that being because being in agriculture in this area, there's farmed area, and then there's also some riparian setbacks where you have to be a certain distance from the stream to disturb it. So 6 meters was about that in that window. With the vertical well scenario, we were looking at an assumption of no interference from other wells, and then with a horizontal well scenario, it assumes a linear system of wells. And then we just set the simple criteria of what's the maximum pumping rate we could achieve without drawdown exceeding the alluvial aquifer thickness. So here's the study area. 15 Mile Creek, the squares represent test pits, and the blue squares are the alluvial wells, and then the triangles are where we perform cylinder infiltrometer tests. So fairly well distributed across this approximately 9-kilometer section of the area of the watershed. So going into results, what we found here was quite consistent up and down the watershed with silt loam, sandy loam material from down to about 1 meter depth, and then finding increasing sand and gravel with depth. Generally at the bottom, at about anywhere from 1.5 to 4.9 meters below ground surface, we encountered either basalt or a cemented sand layer, which was effectively the bottom of that, the hydraulically restrictive layers that were at the bottom of the alluvial aquifer. So based on this, it was a fairly shallow or thin alluvial aquifer of 1.2 to 1.5 meters thick, which immediately that raised some red flags about, okay, are we going to be able to pump what we need out of the alluvial aquifer to achieve the recharge over that short period of time. Laboratory testing confirmed what our logs were, but primarily we also, from the hydraulic testing here, we have a 6-inch diameter core that we were repack core so that we can include the gravels. Above the alluvial aquifer was 3.8 times 10 to the minus 4. Within the alluvial aquifer was about an order of magnitude greater KSAT. The test wells, we went to pump on the wells. We had hoped to be able to pump on the wells and to induce flow from the creek, and then to be able to collect samples and see how that reflects compared to the surface water. What we found is when we pumped at a very low rate of 11 liters per minute, we desaturated the well. And we didn't have a pump that could go any lower on hand at the time. So what we then did is a slug test and came up with a mean horizontal saturated hydraulic conductivity for the alluvial of 1.5 times 10 to the minus 4 centimeters per second in that case. And then I mentioned cylinder infiltrometer. So this is looking at field saturated infiltration, so near surface infiltration rates, which helps to guide the sizing that would be required for a surface basin, an engineered basin, to be able to recharge and treat the amount of water we're looking at. And it was quite variable, the effective KSAT, ranging from 1.2 times 10 to the minus 2 centimeters per second to as small as 7.1 times 10 to the minus 4. And that varied based on soil texture. There was 4 primary soil textures in this area, so quite a large variability in the near surface conductivity. So pulling all this information together, then we applied this into the analytical model that I mentioned. We found on average that the saturated thickness was 1.5 meters. We used a best case alluvial aquifer KSAT of 1 times 10 to the minus 3, so this was the highest that we measured. And why I point that out is because then running this with a vertical well, again looking at over 14,000 liters per minute is what we're looking to collect. Running this analytical model with these parameters, a single well could only achieve 2.7 liters per minute before drawdown would exceed the thickness. And so that would require over 5,000 wells needed, which, again, it's not possible that we would do that. Likewise, with the horizontal well system, we would need over 12,000 linear meters of horizontal well in order to collect the amount of treated water. So that analysis knocked out alternative 1 and alternative 2. And so where that leaves us is alternative 3, which is an engineered solution diverting water into a spreading basin with a collection, subsurface collection. Now, so running some calculations based on our lab measurements and cylinder infiltrometer near surface measurements, and with the assumption that 80% of the recharge water a basin applied water would be captured by this underdrain system. Now that's going to be based on the design of your system, the depth of the collection system, the spacing between collection pipes, but based on some work we've done at Orange County Water District and other areas, 80% was a reasonable assumption. We found that we would need anywhere from 7.7 hectares to as small as 0.2 hectares of infiltration basin. Now, they could be spaced out. It doesn't have to be a single basin. They could be spaced out, multiple basins. But nonetheless, we see very sensitive, quite a large variability, and that's a next step is to narrow that down. Now, looking at water quality results, surface water quality was actually quite good. Primarily came back with coliform bacteria and, of course, suspended solids. Both we want to treat because to reduce the potential of clogging of the injection well, and then also for regulatory purposes. I mentioned we were unable to collect a sufficient shallow aquifer sample just because we couldn't pump. We didn't have a low volume pump with us, so unfortunately we couldn't do that. But again, I think based on all the work that's been done in the past, work we've done, work that others has done, work that's been presented over the last 2 days, we feel fairly confident that aquifer filtration will reduce the suspended solids and the bacteriological constituents to the point that it would need to be done. However, we still need to perform a small-scale pilot testing with the basin to prove that up. So conclusions and next steps, again, vertical and horizontal collection wells are not feasible. We determined from our characterization and modeling. Passive infiltration with a collection basin potentially is feasible, likely is feasible. We have some data gaps in that we need to get a better handle on the variability of the near surface KSAT as well as alluvial aquifer KSAT, because an infiltration basin is likely not going to be right adjacent to the stream, because otherwise you just have return flow directly to the stream. That's going to have to be off stream more, and we did not focus our characterization off stream. So we need to check and see if the alluvial aquifer characteristics further off stream are similar. And then again, the aquifer filtration effectiveness. So essentially, our next phase is to identify potential sites to do this pilot study by looking at near-surface KSAT data, what conveyance costs would be, land acquisition, leasing, and right-of-way costs, and then compatibility with land use and ownership. And from that point, we can narrow down to certain parcels that then we can go out and do more testing to better characterize the near-surface saturated hydraulic conductivity, and then from there, hopefully perform a pilot study. So with that, I'd like to acknowledge our funders for this project, the Wasco Soil and Water Conservation District, and grants from the Oregon Watershed Enhancement Board and the state of Oregon. So thank you.
I'm with the water supply company, and
Okay.
in our situation we see that if we distribute water for more than 1, 2, 3 kilometers, it will have the temperature of the surrounding area. So if you drop cold water somewhere upstream, will it not be warm at the point where the fishes needed it?
At some point, well, that's a good question, and that's something that would need to have some modeling to take a look at as you move downstream with this cooler water. How far downstream does that cool water positively influence the temperatures? And that would need to be evaluated further. I think there have not been there was also a separate study done looking at a surface reservoir, which of course that is going to be warmer water reduced to the stream, as opposed to the water that was stored in the aquifer. And they did some surface temperature modeling, and I think they looked at the influence of that, how far downstream that went. I'm not familiar with those results though, but I think it is something that we need to take a closer look at and see.
Okay, thank you.
Mm-hmm.
All right, if you would join me in thanking Jason for his talk.